Earth is the material after which our planet is named. We usually walk or build on it without due attention to its key role in sustaining life. Through urbanization and environmental degradation, soil is lost for the production of food, fiber, and timber.
Soils provide the foundation for our daily lives. They are essential to feed us. They filter our drinking water. History has shown that every civilization that did not protect their soil has inevitably collapsed.
But which soil types must we protect to sustain our civilization, and where are they located? ISRIC, World Soil Information in the Netherlands, collates and maintains reference samples for the world's major soils. It also holds over 6,000 soil-related maps, a real treasure and unique resource. The maps are being scanned and the underpinning soil data digitalized. However, additional quantitative data and new analysis techniques are needed for production of a new global soil map by a large international consortium, as explained by Dr. Hannes Reuter of ISRIC.
The ultimate aim of the global soilmap.net project is to help feed 9 billion people in 2050 by generating quantitative soil information at a high resolution.
Until recently, most soil maps were qualitative. That is, soils were given a descriptive name, for example, Cambazole or Regosol. Worldwide, there are 32 major soil reference groups, each of these having different properties and suitability for crop production. The new global soil map contains much more information, quantitative information.
Most of the data were collected and analyzed some 30 to 50 years ago, while relatively few new data are being collected these days in view of the high cost of conventional sampling approaches.
Colleagues from the Center for Environmental Research in Leipzig, Germany, are collecting new data for global soil map using less expensive methods. These allow a much more precise characterization of soil properties and at a much greater depth. Dr. Ulrike Verban and her colleagues are using soils from a long-term field experiment in Bad Lauchstädt. This is one of the oldest agricultural experiments on Earth. For over 100 years, all field management practices and their effect on soil properties have been recorded.
Due to the long-term use as a field experiment, we can observe differences in organic carbon content within each plot. This parameter is of interest to us, and we would like to test whether we can also identify these differences with our sensors.
Using a mobile gamma spectrometer, the scientists measure the radioactive decay of the different elements in the soil. Clay content is an important parameter of water retention capacity, the amount of organic matter as well as the soil's ability to sequester CO2 from the atmosphere.
Clay content is also important for the farmer, as it is an important parameter of soil fertility. From a research perspective, we are interested in clay content as it allows assessment of how different erosion types might affect a specific soil.
Clay content of this black soil has been known for 100 years. Therefore, Dr. Verban can assess whether their gamma spectrometer measures it correctly. Researchers from Leipzig also take soil samples for the laboratory. The rest is done by computer. Relationships between the laboratory and gamma-ray determined clay content are plotted. The clay content for many locations in the field may be estimated. Less input, more data.
Similarly, some of our other sensors may be used for airborne observations. Therethrough, larger areas can be mapped more efficiently, using a limited amount of laboratory-analyzed soil samples for validation.
The procedure developed in Leipzig allows for a more efficient investigation of soil properties at a greater depth. Currently, 10 different soil properties are being estimated at 6 reference depths. Results of worldwide analyses are being incorporated in a first version of Global Soil Map product at ISRIC.
This is an example of how we have visualized soil profiles with different soil property distributions. We have used this information together with novel geostatistical methods to create soil maps. The example for Nigeria shows the organic carbon content for 0 to 5 cm, 5 to 15 cm, and 15 to 30 cm depth.
A complete picture of the Earth, fertile and vulnerable. The biggest enemies of the soil in the developing world are natural disasters and an inefficient agricultural system. In the Western Hemisphere, many soils become sealed through urbanization and as such are lost for productive agricultural use. In 1988, German politicians already called for a European Soil Framework Directive, but up until today, this directive has not been ratified. Attention for soil protection lags behind that for climate change adaptation and mitigation, while soil plays a major role for any future generation. Similar to water and air, soil is an easily damaged natural resource. Results of global soil maps support science-based planning and are of utmost importance.
We are anticipating that a lot of decisions in the future will be based on being able to access our data in a known format, in a numerical format, and simply ingest it into models of dynamic processes like carbon sequestration or runoff or crop growth, and to decision-making algorithms. So, how much good land do we have, and therefore how much productivity can we expect to get?
The soils of our Earth are a natural treasure that we absolutely need to conserve for future generations.